what do you remember from our last lesson?
Can I rather have a question? I don't know. What do you remember feels a bit general. I remember that sigma is what represents the sum of a sequence. The number on top of sigma is let me start with the number on the bottom, which is I. I is usually the number of the first digits of the sequence. And then next to the sigma sign is the sum of the sequence. Like if it's 2i, then you know you're multiplying by like you I'm sorry, I'm bad at explaining. And then but it'll be like 2i, which is the sum of the sequence or the equation for the sequence, not the sum. And then on top of that, on top of the sign of sigma, it's the last digit that you should get.
Okay. Is that all?
Yeah, as I said, I'd prepare a question. I do remember things, but I don't know what you want me to say I remember.
Okay, so so everything that I've heard sounds correct, but that was the previous lesson before our last lesson.
Really?
Yes.
Because
we were doing this one where we had to prove that this is equals to this.
Oh, I have a bad memory. I don't remember that.
Okay, it's fine. Okay, so let me check. Let's just check the presentation, right? Then I'll explain in brief, not take a lot of time. So if you remember, we talked about the domino effect, right? Because we were saying we want to prove a certain statement is a mathematical statement is valid for any integer that we insert into the formula or the statement. So we said that since we cannot verify for each individual number, we cannot like verify if we insert one, just like what we were doing when we were doing sequence, right? Like you were saying, when we were doing sequence, we would put a certain term that we are told to put in, like find the second term. That means we have to put 2 into the formula if it starts from 1, right? And then we go to we'll go 1, 2, 3, 4, 5, 6, right? But now there comes a problem whereby we don't have enough time to test every number, if we are going to get the same, if our statement is going to be exact, right? So that's why we said using mathematical induction, we use a concept called the domino effect, meaning if I can prove that the first one or the second one is true, then that means all the other integers are also true, so that we don't waste our time trying to insert 100,000 or 100,001, 100,002. Then we go to 2,251,352. We'll be taking forever. I guess you have that idea. So we are saying if we can prove it for one, or if we can prove it for one, that will mean it would assume that all the rest are true, since we have proved for the first one, which is not always true, but for the type of questions that they'll be asking you, yes, it would be true for the. So that's where I gave this question, right? If you remember this question, we said what is the next number in the sequence? If you remember, you said what?
I had said 32.
You said 32, and I said there's another answer, right?
Yes.
What other answer?
31.
31. And where I got 31 was from bisecting the circle into how many times? 1, 2, 3, 4, 5, 6, 6 times. So I was cutting the what we call the circle 6 times, and also every time I cut, I join what you call I join, or let me rephrase. So I took a circle, and every time I put a new point, I'll join it to the previous points that were already in the circle. So we ended up getting 6 points, and then those 6 points, when we counted all the parts that were all the parts or shapes that were contained in that circle, we came up with 31, which is what they call the Moses circle, right? You remember that?
Yes.
Okay, cool. Then we went to this question where we said, if you look at the numbers between 1 and 10, which number is missing, and then we noticed that 7 was missing, right? And then we said, so from 1 up to 100, how many non-7 numbers will we have? And then initially we said would how many we said would miss
Yes,
those. We said that
it's
we get yes
it's at 9.
90. Yes, we said 90 because we times by 10 since it's from 1 to 100. Which was an assumption, since it's true for the first what you call for the first range of numbers. That means it's going to be true for the next 10 sets of numbers, for the next 9, I mean, sets of numbers. So that's where we ended up getting wrong again. Well, that's where we getting wrong again. And then we forgot that 70, 71, 72, 73, 74, 75, 76, 78, and 79 were included in the numbers that had 7. So we were just counting 7, 17, 27, 37, 47, 57, 67, 77, 87, and 97. That's why we got 90 instead of 81. Do you remember this one?
I remember.
Okay, cool. Then we went to the third question, saying that we have a sum of odd numbers, and if we add them, it's equal to the number of odd numbers that we added to the power 2. So since we have 1, it's equal to the number of odd numbers that we have here, which is 1 to the power 2. Same thing here, 1 plus 3 is equal to 4, which is equal to the number of odd numbers that we added, which is 2 to the power 2. And we go all the way there. Then I asked the question, do you think this works? And do you remember the answer that you said? What answer did you say? You
I
said
said
it works.
yes.
Yes. So after that, that's where we talked about saying yes, that this works. or all square numbers, and we showed that it can be represented in sigma notation or summation notation. Why does it? Why can we show it in summation notation? If we go back, it's because we are adding. We're adding. We're adding new terms, new terms, new terms, adding new terms. So meaning that we can use the summation notation that we learned from sequences and summation notation, right? Uh, or it can be expressed here in expanding notation, which is like this. So so yeah, so since we said yes, right? Since we said yes, it works. Now we have to prove it works. Now you have to give a proof. Now you have to tell like your lecturer or your peers that no, I believe this works for every integer that we insert into this scenario or formula or summation notation, etc., etc. So that's where mathematical induction comes in, whereby we have to prove that this works for or whatever integer value that we put into it. Make
Mm-hmm.
sense?
Yes.
Okay. Do you have any question?
No.
No. Okay. Cool. So, so I was thinking, let's just redo, right? All the examples. Let's just redo all the examples. A mathematician mustn't be, what you call, mustn't run away from doing questions, even if you have done them before. Who knows? You might have gotten it correct yesterday, but today, if you try it, you might fail. So you always have to have like that type of mindset, which a lot of people don't really have, because when they see something that they are already gotten correct, they wouldn't want to do it again or work it out again, which
Mm-hmm.
which is very which is very risky, because what if you don't remember and you get a similar question in the exam and you get it wrong? So yeah, so we're going to do the examples that we did, and I hope, yeah, it will make more sense this time. So we have this statement, right? We have this statement, and we are using, it says use mathematical induction to prove the following statement for all positive integers n. Okay, so now, we have 3 steps, right? So the first step is to prove for n is equals to 1. That is the first step, right?
Mm-hmm.
Yeah, maybe if you can write it down so that you can also so that it can be, if you forget, you can easily see it. So we are proving for n is equals to 1 first. After we prove for n is equals to 1, we prove n is equals to k, right? But this step, right, you can say here you fully prove, right? For the first one, when n is equals to 1, you fully prove. That means at the end of the statement, you say n is equals to 1 is true, right? But when n is equals to k, you say partially prove. Partially prove. Why? Because you are going to use this, whatever you get when n is equals to k, and you're going to use it for step 3. So you're going to prove for n is equals to k plus 1. and that's where the partially comes in. And then you're going to use a statement from n is equals to k, and you're going to take it as it is, and then you're just going to insert it when you're proving for this. And then once you have done that, now you have fully proven for the whole question. Does that make sense?
Yes.
Okay. So we have 1 plus 4 plus 7 dot dot plus 3n minus 2 is equal to n over 3n minus 1 over 2. Okay, so now we have to prove. So what is the first step? What is the first step?
It's proving for n equals 1.
So proving for n is equals to 1. So when we say for proving for n is equals to 1, we can say you can write for n is equals to 1, and then you do your working. Others would literally say, let this whole thing be, they'll say, let this whole thing be p of n. So they'll represent it as a function. So that means if now it's represented as a function, that means when they write, when for n is equals to 1, they'll just write p1, right? Which is I think it makes sense since we did functions. So it makes sense. If we are finding for k, they would write pk. If we are writing for k plus 1, we will write p of k plus 1. Okay. So you could literally use any of those, depending which one do you prefer. So I would stick with this personally. Yeah. So for n is equals to 1, so we have a left-hand side and right-hand side, right?
Mm.
So we deal with them separately. We kind of deal with them separately. So which one do you want to deal with first?
The left-hand side.
The left-hand side. So now you write left-hand side is equal to, and then on the left-hand side, since we have this formula, right, which is used for every term that we have, starting from n is equals to 1, right? Because it always starts at 1. Why? Because we said mathematical induction works for integers, right? Integers, and 0 is not an integer. 0 is not. So meaning that the smallest integer that we can have, and no, not integer. I'm mixing. Sorry, it's not integer. It's, what's the other name? We have integers. We have whole numbers. Whole numbers. Yes, that's the word that I was looking for. Whole numbers. Okay. So just, yeah, so every time you just know that when n is equals to 1, we always use n is equals to 1. So we take the formula, right? If you want to take the formula, it's fine. But yeah, or you, yeah, I think it's very safe to use the formula. So you take the formula 3n minus 1, and then you replace where n with 1, where n is with 1. So 3 times 1, we get 3 minus 2. Then 3 minus 2, what do we get? We get 1, right? So that's the left-hand side. Let's check what the right hand side has to offer. So now we write right hand side here is equal to, and then we take the right hand side, right? And then we replace wherever there's n with 1. So we write 1, open bracket, 3 times 1 minus 1
all over 2.
all over 2. So let's check. 3 times 1, we get 3, minus 1, we get 2. So 1 times 2 over 2. And then what do we get?
Excuse me, 1.
We get what? 1, yes. So here, since they are equal to each other, so you write for n is equal, or you write the statement is true. Statement is true when n is equals to 1, right? So since you have proven left hand side is equals to the right hand side, cool. Okay, now we go to the second stage. What is the second stage?
It's proving for n equals k.
Proving for n is equals to k. Okay, so now we take so proving for n is equals to k. So for this one, we just write, so for this one, for n is equals to k, we just write the whole statement as it is, but replace where n is, right? So for n is equals to k, we write 1 plus 3, 1 plus 4 plus 7 plus 7 plus dot 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 plus 3, was it 3k minus 2 is equal to k open bracket 3k minus 1 over 2. Okay, any question?
Mm.
No question.
No.
Okay, so once we do this, we are already done with step 2. So step 2, you just do this, nothing, you just write it and just replace n is equal to k, then you are done with step 2. Now we go to step 3. So what is step 3?
Prove for n equals k plus 1.
So for n is equals to k plus 1. Okay, so for n is equals to k plus 1, which side, okay, which one do we use first? I think, which side do you want to use first? Let's check if it changes anything.
Left side.
Left hand. Okay. So what we do for the left hand side, so I'm going to just explain what I'm going to explain. So for the left hand side, isn't we are saying 1 plus 4 plus 7 plus dot 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 plus 3k minus 2 plus 3k plus 1 minus 2. Okay, so I want to ask, what is the difference? Let me use a different color, maybe black. What is the difference between this statement and this statement? What's the difference between those two?
The difference is this one doesn't is not equals to k over 3k minus 1 over 2. Instead,
Okay, but okay, which is correct, but we are not including this in in the explanation.
I think I must give another reason.
Yes.
Um, mm, I don't know.
Okay. Look again and see if there's anything different between the two. Because if they are not different, that means they have to look exactly the same.
We added 1, 2, 3k minus.
So you are talking about this term.
Oh, sorry, I didn't realize. I think I'm missing myself by mistake. I was saying that yes, it's we added 1 to the 3k minus 2, so it makes that different.
Okay. So the difference between yeah, true. So the difference between this and that is that we added a new term, k plus 1 term, right? K plus 1 term. So since we have since we have this, right, since we have this scenario, we are supposed to replace these guys with this one. Any question there? So we have to replace those guys with k open bracket 3k minus 1 over 2. Any questions? Since we said they are equal to each other, so we can do that. Any question there?
No.
Okay, cool. So now we have, so you check k open bracket 3k minus 1 over 2 plus 3 open brackets k plus 1 minus 2 in brackets as well. Okay, so we now have this, right? We have these two guys. Now we have to add them, right? We have to add them together. So now the question is, okay, so now you have to now take out your book, you're working where you're writing, and I want you to simplify this.
It's 3k plus 3 minus 2, which is equal to 3k minus 1.
Okay, you said what?
3k minus 1.
3k minus 1. No, it's not 3k minus 1.
Oh, I mean plus 1.
Yes, 3k plus 1. Okay. Okay. So we have, let me write it down. So we have 3k plus 1, right? And k, 3k minus 1 over 2. Now we have to add these two together. Now we have to add them together. And it should be a fraction. So what would it give us now?
It'll be k times 3k minus 1 plus 2 times 3k plus 1 all over 2.
Yes. Okay. And then if you simplify, what do we get?
3k squared minus k 3k squared minus k plus 2 times 2 is k plus 1 2 3k squared plus 5k. It's 3k squared plus 5k plus 1.
Plus 1.
Oh, plus 2. Ish, why do I
Yes.
keep doing that? Plus 2.
It's okay. I was thinking maybe I'm wrong.
No.
Okay. So, okay, plus 2. Then what do we do? We have 3k squared plus 5k. We said plus 2. What do we do? That's where we have to check if it's factorizable. We have to factorize. So always do this if we have to check if it's factorizable. And in most cases, yes, it would be.
So do you want me to factor it?
Yes, I do.
Oh,
Yes,
no, I made a mistake. Sorry. Just start again.
it's okay.
Mm-hmm. It's 3x plus 2 times x plus 1.
Okay, so it's 3k plus 2.
Oh, yeah. So
It's
this to
okay.
working with k. 3k
3k
times k
plus
plus
2
1.
times k plus 1. Right. Can we simplify this further? Yes or no?
No.
No. Okay. So this will be the answer for our left-hand side, right? Okay. Now we have to deal with the right-hand side. Okay, so we now go right-hand side is equal to, let's check. So now the right-hand side, we write, going all the way. So k plus 1, open bracket, 3k plus 1 minus 1 over 2. So we write k plus 1 times 3k plus 1 in brackets minus 2 over 2. And now we have to simplify this. So if we simplify this, what do we get?
3k squared plus k minus 2 all over 2.
Okay, so so uh, so there you kind of went a bit wrong, or you are not wrong, or I would say you're not wrong, but you kind of did something that kind of wasted time a bit. Why? Because if you look, okay, so why am I saying that? I'm saying that because I think we are only supposed to simplify this bracket, not the whole
Oh, because we're going to
numerator.
factorize again.
Yes.
Um, so it's k plus 1 times 3k minus 2 all over 2.
So what did we get?
3k.
Oh, sorry. I'm realizing something. Here's supposed to be 1. Let me double check. Yeah, it's supposed to be 1. It's right there. Okay. So yeah. What did you say the answer was?
3k minus
3k
1. Oh, I have to do it again
plus.
because
Yes. So
3k. It's 2.
okay, plus 2 over 2. Now, does this look like the left hand side?
Yes.
It does. Are you sure it looks like?
Almost exactly. The top brackets are just the other way around.
Swapped. Okay. No, but yeah, in such a scenario, you would say it's exactly because
It's
yeah, in mathematics we
about the
do,
number.
yeah. So so okay, so once you have done this, now you have answered the whole question. Now you would have proven. The only thing that is missing is a statement that you have to write. So you would write this statement is true when n is equals to 1, n is equals to k, and when n is equals to k plus 1. Any question?
Mm-mm.
Mm. Yeah, okay. No question.
Mm.
Okay. Okay, is there any part that was a bit tricky to understand?
I think not tricky to understand, but like sometimes I'm slow to factorize, but that's my own problem. And can you repeat? So this is how we prove
Mm,
the summation.
yes, this is how we prove the summation of certain, yeah, for summation, we would say.
So by proving n is equals to 1,
Mm,
then
then
may
n
you
is,
please put it in like, can you please put what we've done completely in words? Like by proving n equals to 1 and then proving this is how it proves the summation.
okay, uh, so, okay, so, I think, I'm not sure if I understand, but let me try. So this, by using this method, we are first proving that n is equals to 1, right? But proving it by n is equals to 1 is not enough, because there can be another number. For example, n is equals to 3. If we insert it, then our what you call our statement will not be true. When we enter here 3n minus 2, it will give us 6 or a certain number. Then if we enter the same number here, 3, it will give us 10. So by writing n is equals to 1, we've proven that it's correct. It's not enough. Now we have to replace, now we have to prove for n is equals to k, which covers like any general number. And then we have to prove for n is equals to k plus 1. And n is equals to k and n is equals to k plus 1, they help each other. Especially n is equals to k helps n is equals to k plus 1 to be proven. Why? Because we kind of bypass, we kind of take a statement from n is equals to k, then insert it as n is equals to k plus 1. And then once we have proven everything, this now tells us that our statement is true, no matter what value that we put it in the for n. So whether we put hundreds, whether we put a million, our statement will always be true.
Okay.
Does that now make sense?
Yes.
Which kind of is opposite from the first questions that we were doing, like for example this one, where which kind of is the opposite, because here we were using our knowledge of patterns that we have, like our patterns like this one, 16, then we have get 32, but we are not entirely true on that case. And also here in question number 2, where we thought, well, since there's 1 7 missing, that means there are 10 7s missing in from 1 to 100. So now you see the scenario whereby if you have the first few statements which is true, that means it doesn't really mean that it's always going to be true. But since now we're using mathematical induction to prove our statement, now the overall thing is that no matter what value I put into this equation, it's not going to break. It's still going to satisfy my left-hand side and my right-hand side.
Okay.
Okay. Does that make sense?
Yes.
Okay. So yeah, every time you see a question like this, you just be proving. Just be proving. There's nothing else. Just prove. Yeah. Any other question?
No.
Okay. Okay. Cool. Now let's, since we have gotten the gist of that, let's now deal with proof that 1 times 2 plus 2 times 3 plus 3 times 4 plus dot 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 plus n times n minus 1. Actually, it's n plus 1. Or is it n? Yes, it's n plus 1. Is equals to n times n plus 1 times n plus 1 over 3. So here, I made a typo. I remember I made a typo here. So it's n and then times n plus 1. So now what do we do first?
We prove for n equals 1.
Okay, so for n is equals to 1, what side are we dealing with first?
Left-hand side.
Left-hand side is equal to, what do we write?
Left-hand side is equals to n or 1 is 1 times 1 plus 1.
1 plus 1. Okay. Then what do we get? Overall.
2.
2. Cool. Okay, so we've proven the left-hand side. Let's prove the right-hand side. Okay. What do we write for that?
This is 1 times 1 plus 1 times 1 plus 2 all over 3,
Over 3.
which simplified, it's 2 times 3. 2 times 3, which is 6 over 3.
Which will give us
2.
2. Yes. Which will give us 2. So now what do we write? What statement do we write?
We then write statement is true when n equals 1. This statement is true.
Yeah. The statement is true when n equals 1. Yeah. Okay. What's next?
We partially prove for n equals k.
N is equals to k.
We then say, can I see the equation? 1 times 2 plus 2 times 3 plus 3 times 4 plus ellipses plus k times k plus 1
Okay.
is equals to,
Let me write that first. Plus 2 times 3 is 3 times 4 plus k plus 1 is equal to
is equals to k, oh, no space, k times k plus 1 times k plus 2 all over 3.
k times k plus 1 times k plus 2 over 3. Cool. Cool. Okay, what's next?
Next is proving for n equals k plus 1.
So for n is equals to k plus 1. Okay.
It will start on the left-hand side.
Okay, left-hand side.
We will say 1 times 2 plus 2 times 3 plus 3 times 4 plus ellipses plus k. Oh, plus k plus 1.
Okay, so here I think it's better to write this first.
Okay, k times k plus 1.
Plus 1 plus, that's where you
Plus
enter.
k plus 1.
Then we put in brackets, yeah, and times k
Is
plus 1.
equals times.
Yes, because isn't we have n here, right? So isn't we have n here where the k is, and we replace, so this k is being replaced by k plus 1, which is this. Does that make sense? We have this statement. This is the
Yes.
statement that we are using. So this is from when we are replacing n with k, right? What happens when we replace n with k plus 1?
What happens if we replace n with k plus 1?
Yes,
It becomes k plus 1.
times, because you only say this n.
Oh, times k plus 1 plus 1.
Yes, k plus 1 plus 1. Does that make sense?
Not really, because isn't looking at the sum, right?
Yes.
We
I mean here.
n is equals to k plus 1, right?
Yes, n is equal to k plus 1, yeah?
So shouldn't it just be k plus 1 times k plus 1 plus 1?
Yes, you can do it, but the only thing that you can do it, I'm not, it's not saying that it's wrong, but the question is, will you remember to replace all of this with this guy? Because we are now going to take all of this all the way to k times k plus 1, and we're going to replace it with our the the equivalent to it. So now that will be the question. Will you remember? If you do remember, then from now on we'll just use this.
Ah, I see why I'm confused. I forgot that it has to be the like original k, then you add the
K
new
plus
k plus 1.
Yes, because the new k plus 1 is actually a term after k. That's why it says k plus 1. So it's a new term after k. So just like when we are using the second term, there's a term, the term after 2 is the second term is the third term. So we just took 2 and we add plus 1. So it's the same thing as k and k plus one. Okay.
Yeah.
Any question?
No, I see why I was confused.
Okay, cool. So what do we do next? So question, should I leave next time, the next question that we do, should I leave k, should I involve k, or should I involve k or not? And is this one,
I shouldn't.
I should leave it out.
Wait, what do you mean by leave it out so I know how to answer
As
the question? And then should I like simplify?
No, as in next question that we do when we are reaching the third part, when we are solving for n is equal to k plus 1.
Mm,
I'm asking, when we write our statement, this statement,
mm.
should we write it like this, involving when n is equal to k and n is equal to k plus 1, or should I rub this off and it will look like
Oh,
this?
no, it should be there.
Okay, that's what I was trying to ask.
Mm.
Okay, cool. Since we sorted that out, what's next?
We then oh, now we simplify the
Okay,
list. Mm. We say k into k plus 1. This is k squared plus k plus k.
no, that's wrong.
Oh, sorry, I hadn't finished writing down because I was still confused about.
Okay, it's okay. I'll wait.
What do you mean it's wrong before I continue?
Or you are saying that you simplified this.
Yes.
Yes, that's the part that's wrong.
Why?
because here is where we substitute this whole line. So I then introduce k times k plus 1, k plus 2
Oh, but
over 3. So we do,
then
yeah, then
we
uh,
add the
the k plus 1
k
there.
plus 1 times k plus.
Mhm. Any question?
No.
Okay, cool. Okay, so note that every time we'll be doing this. When we add n is equal to k plus 1, we'll be doing this. Okay, so okay, so let's simplify this side.
It
This one.
becomes k squared plus 2 k times k plus plus 2 k squared. Um, it becomes okay. Wait, let me finish. Six. Three, six, seven, six. The final answer is 3k. Sorry, k cubed plus 6k squared plus 5k plus 6.
Okay, what did you do? Okay. Um,
First, I said k times k plus 1 times k plus 2. Oh, no, sorry, I'm repeating it with the other line.
yeah.
I said 1 times the first part because that's the rule for adding fractions. And then I said 3 times k plus 1, k times k plus 1 plus 1. So k into k plus 1 times k plus 2 is equals to k cubed plus 2k squared plus k squared plus 2k
Okay.
plus.
Sorry. Can I stop you there?
E.
Okay. So the question that I asked, what do we get if we simplify this, not the whole thing?
Oh, I thought you asked me to finish.
Okay. No. 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 I didn't. I was talking
I'm
about something else.
sorry.
It's okay.
I was being forward. That is
It's okay.
3k. No, let me make sure. That is 3k squared plus 2k plus k plus 2.
This one,
Yes.
3k, k squared.
Oh, it's before we add this. My bad.
Yeah.
I'm still being for it. K plus 1, k plus 1 is k squared plus 2k plus
Oh,
k plus 2.
okay. So, uh, so, so in this type of questions, right? We shouldn't always remove the expand. We shouldn't always expand. Why? Because we might be wasting like a lot of time, right? So, okay, what do I mean? Okay, what do I mean? So for example, we have here, right? We can see that in the bracket that says k plus 1 plus 1, we can simplify it further, right? It's not the same as k plus 1 because we can't simplify k plus 1 further, but we can simplify k plus 1 plus 1, right? So we would write k plus 1 times k plus what? Hello?
Sorry, I didn't
So
hear that.
I said, if we are simplifying this, we would get k plus 1 times k plus, so this,
If there's a way to simplify that further. Oh, you
k
mean k
plus,
plus 2?
yes, k plus 2. That's what
Oh,
I'm talking about. So we get k plus 1 times k plus 2, right? So for now, we don't have enough reason to tell us that we should expand, right? Because here, if you expand right now, and if you expand, you you could just make the process a little bit longer than it should be. Especially when we now we go to cubic functions. Now it's more trickier to find the factors. It's a long process. I'm not sure, have you ever done that, factorizing cubic functions?
I, I probably have, just don't remember.
Okay. Uh, it's a long process. So
Um,
what we do, we'll just keep these guys in their brackets, right? Until we are for sure that there's no other way. We have to now expand. So what do I mean now? We say this is over 1, and then we get the common denominator, which is 3. Here we write 3. Here we write k times k plus 1 plus 2 plus 3, right? Times these guys, right?
mm,
Okay, any questions so far?
no.
Okay, so here, right, now we have a question, right? Here we have a question. The question is, do we see anything common in the numerator? Or is there anything that we can factor out on the numerator?
K plus 1, k plus times k plus 2.
Yes, we can factor out k plus 1 times k plus 2, right? So if we factor out k plus 1 times k plus 2, what are we left with?
K plus 3.
K plus 3 over
3.
3. Okay. Can we simplify this further or not?
No.
No. Then that would be our answer. So if we had expanded like here, or even expanded these two when we're adding, like right here, that will mean that we wouldn't get to this stage in a shorter manner. We would be taking like an extra page or 2 pages just for us to get back here. Which is kind of counterintuitive, because normally when you see it some like in this manner, your first instinct is to expand, and it should be x squared plus what does it give us? X squared plus 3x plus 2. I mean, k squared plus 3k plus 2, right? That would be your first instinct. But here in this mathematical induction, we shouldn't always go that route. We have to just make sure we check, is there anything that I can factor out. I guess we also did something. Did we do something like that here? No, in this. So if you check also here, we did the same thing. We had 3k plus 1 minus 2. Then we simplified here. Then we got 3k plus 1. We didn't expand, or you would say no, we can't expand this, which is fair enough. Then we made them into a single fraction. And then in this scenario, because 3k plus 1 and 3k minus 1 are not the same, they're different, so we can't figure out anything. So we are forced now to expand these those brackets. Does that make sense?
Yes.
Okay, cool. So now this is the left hand side, right? Okay, what about the right hand side? What do we write on the right hand side?
The right hand side is going to be where is it?
So here.
Yes.
Mm.
It's going to be k plus 1 times
You said k plus 1.
this
Okay, times
k plus 1 plus 1
times.
times k plus 1 plus 2 all over 3.
Okay, so let's try to add that down. Right hand side is equals to k plus 1 in brackets, k plus 1 plus 1 brackets, k plus 1 plus 2 in brackets over 3. Okay, then what?
Sorry, I'm still writing. And then we say k plus 1 times k plus 2 times k plus 3, and we're done.
Times k plus 3 over 3. Okay.
All over 3.
Can we simplify this further?
No.
No. Okay, so let's check if it is the same as our left hand side. Is it the same?
Yes.
It's the same. Okay, so what do we write now?
Then we write the statement is true when n equals 1, n equals k, and n equals k plus 1.
1 n equals k, n equals k, n equals k plus 1. Right. Okay. How is this one? How is this How's this question?
That's fine, yeah.
Okay,
Now that I understand.
okay, cool. Now we have to go to this one. So for n is greater than.
Cool.
Okay, what do we do?
We first start with proving if for n equals 1.
N equals 1. So for n equals 1. Mm-hmm.
And then we say that the left hand side is equals to 3 to the power of 1.
3 to the power 1. Okay,
Yes.
cool. Which is 3. Or we could say what? What is the other way we could do it? We could take the formula and add 1 into the. Oh no. Oh no, sorry. I'm taking the wrong side. Sorry. So 3 to the power 1. Sorry. Took the wrong side. Okay, cool.
Then we say the right hand side, we substitute in
Okay.
for 1, we say 3 to the power of 3 times 1 plus 1, or minus 3 all over 2,
Mm-hmm.
which is then equals to 3 to the power of 4 minus 3.
Minus 3.
Yes,
Yeah.
yes, yes.
Sorry. Did you say something?
Yeah. Did I forget an exponent law? Oh, no.
Exponents.
I think I'm confused about the exponents.
Exponents. Yeah. Okay. What way? What were you thinking?
Because
Hello.
hello,
Okay. So, are you saying that there's no law that you can think of,
not
or
necessarily.
or you or you are not sure if there's a law or not?
Yeah. So what
Not
you
sure.
did?
Okay. There's no law here. There's no law.
There's no law.
Yes, of exponents.
Okay. I'm asking, how did you get 2?
2.
Hunt? Yes, hunt is
Yeah.
3 times 1 plus 1.
Yes. Oh, plus 1. Oh, sorry.
Yeah, that's what I was confused about because I'm like, huh? Squared. I thought I forgot my
Wait a bit.
exponent laws.
Wait a bit. I'm coming.
Okay.
Okay, I'm back. Sorry, I didn't. Sorry. Sorry, my mistake. My
Mm.
mistake. Okay. You're supposed to, yeah. If I make a mistake, you should say, I think you made a mistake here.
Oh, but I didn't think you made a mistake. I thought I was the one who's crazy.
Which turns out that I was the one who made a mistake. So,
Mm.
yeah. Okay. Okay, cool. So, what do we do?
Mm. We didn't say. Mm.
Yeah.
I think I'm having a. Now I'm confused.
Oh, no, I understand why you're confused. I understand. I think I know why. Okay, if you put here, if we put 2, what answer would you get?
We're gonna get 6.
We'll get 6 or 3 because we'll get 9 minus 3, which will get 6 over 2, which will give us
Yes,
3.
which will give us 3.
So, yeah. So, and yeah, I think it makes sense now. It's negative. Okay. So the problem was there's a positive where there's supposed to be negative.
Mm.
So that's the problem. Okay. So meaning in my mistake I was correct. Yeah, yeah, but yeah. So we get 3. Okay. Any question?
No.
Okay, cool. What do we do next?
Mm-mm. We then prove where n equals k.
N is equals to K. Okay, what
Yes,
do we
then we say
write?
3 plus 3 squared plus 3 cubed plus ellipses plus 3 to the power of n.
3
I
to the
mean,
power
to a power of k
is equals to
is equals to
need to check.
3 to the power of 3k minus 1 minus 3 all over 2.
3k minus 1 minus 3 over 2. Okay, what do we do next?
Next, we prove n is equal to 1.
Well,
N is equal to k plus 1. I don't know what I just said.
k plus 1.
Mm-hmm. Then we
Why
say
do we
that
write
the left-hand side
is equals to
is equals to 3 to the power of k plus 1.
3 to the power of k plus 1?
No, 3 to the power of k plus 3 to the power of k plus 1.
There's something missing in that statement.
Mm. Oh, it's 3 plus 3 squared plus 3 cubed plus ellipses
Plus
2 squared plus
3.
3 cubed plus ellipses plus 3k plus 3k plus 1.
Yes, correct. Correct. Okay, what do we do now?
Now we say in 3k minus 1, 3 to the power of 3k minus 1, minus 3 all over 2,
Mm.
plus,
Plus,
excuse me, what was I saying?
we say it's 3 to the power 3k minus 1 minus 3 over 2
Plus 3k plus 1.
plus 3 to the power k plus 1. Okay. Any confusion here?
No.
Okay. So now we have to simplify. So yeah, let's see what we get.
I think we take out I don't know.
Okay, let me see my side.
Do we take out 3?
Oh, you're saying we take out 3
I'm asking, do we?
from k minus 1. Which could make sense, but the only problem is that we have k minus 1 k plus 1. Let's do this. There must be something wrong with this question. Either the formula, because now I'm thinking, how can I join this and this? It would have been easier if we had k plus 1, because we could separate or we could separate. No, kind of tricky. I think it looks like it's 3k minus 1 minus 3. It's over 2, 3 to power 3k minus 1 minus 3 plus 2 times 3k plus 1. Something's not adding up here. Okay, we'll check it. We'll check it out. Something's not adding up. Is that the last one? Okay, let's do this one.
So we're giving up?
Okay, let me check where I took it from. This one is B3, so it's should be from the workbook. Because I think maybe we correct in the first place? Oh, okay. Can you see?
Yes, but
Here. Okay.
we had changed it because you thought it was wrong, so that 3K can
Sorry?
be 3. I'm saying we had changed it, remember, because you thought it was wrong because of the 3 squared
Yes.
situation.
Yes. So actually it's not 3K plus 1, it's actually K plus 1. Okay, so maybe we should try it from the beginning and let's see if we will be able to nail it. So from the beginning, okay. So starting from scratch, right?
Mm.
Okay, so we are now saying that it is it's not responding. Where's my mouse not responding? Okay. Are you still there?
Yes.
Okay. So we are now saying, okay, so we're starting from scratch, right? So we're now saying is equal to 3 to the power n plus 1 minus 3 over 2. Okay. Okay.
Yes.
Hello. Okay. So let's start from the beginning. What do we do?
First, we do proof for n equals 1.
N equals 1.
And then you say 3 to the power of 1 is equals to 3.
What side is
The
that?
left hand side.
Left hand side is equals to 3 to the power 1, which is equals to 3. Yes,
The
right.
right hand side is then equals to 3 to the power of 1 plus 1 minus 3 over 3,
Um,
which is equal to 3 squared minus 3
3 squared minus 3.
all over 2, which is equals to 6 over
Yeah,
2, which is 3.
which is equals to 3. Okay. What do we do?
Then we said, oh, we forgot to say statement is true when it's n equals 1.
Yes, the statement is true. Is true when n is equals to 1. Okay. Next,
Next, we prove for n is equals to k.
n is equals to k. Yeah.
Let me say 3 plus 3
What do
squared
we write?
plus 3 cubed plus ellipses plus 3 to the power of k
3
is
to the power
equals
k.
to 3 to the power of k minus 1 minus 3 all over
K plus
2.
over 2. Yes. Okay. Um, what do we
Now we
prove
say
now?
prove n is equals to k plus 1.
So for n is equals to k plus 1.
And then we say the left hand side is equals to 3 plus 3 squared plus 3 cubed plus ellipses plus
Plus
3k
3 to the power k
to 3 plus 3 to the power of k plus 1.
plus 1. Okay.
And then
Yeah.
we say this equals 3 to the power of k plus 1 minus 3 over 2 plus 3 to the power of k plus 1.
Okay. Then
This is then equals to if we take out 3, we say I want to say take out 3 to the power of 1 and say 3k minus 1. No.
3k. Sorry, you wanted to say
3 times
no.
3 to the power of k minus 1.
Okay, 3 times 3. Do we want?
I don't know.
No, let's avoid that. Should we need that? We need that
Then we
because
say 3k plus 1 minus 3 plus 2 times 3 to the power of k plus 1 all over 2.
okay. So from this, what do we do?
From there, we say 6 to the power of k plus 1.
It's not 6 to the power k plus 1 because 2 cannot multiply 3 because of the power.
Oh, then it stays like that.
Okay, so in this scenario, you group like terms. So can you see the terms
So
that are
3k plus 1 times 3k plus
2?
plus 2.
Yes, because we are saying this and this are like terms.
Minus 3.
As minus 3
2.
over 2. So what do we get?
That.
This.
Now we've proved the right hand side. Oh, you're saying I have to simplify that?
Yes, we have to simplify. It's not enough.
Let me see.
Or what we can do, let's say you are in this scenario and then you are not even sure, right? You're not even sure. What I would advise you, right? Let's say, for example, you have reached here, right? And you're not sure if this is the answer, right? Because there are certain scenarios like the ones that we're doing above where you are totally sure that this is potentially the answer. But you reach here and you're not sure. What you can do is you can leave a space, right? You can leave a space and then do the right hand side. Because when you do the right hand side, you know the right hand side is actually the guides that will help you get to the answer. So the right hand side is actually the if you want to know which answer you are going to, you actually use the right hand side. Okay, so let's do the right hand side. So for the right hand side,
So right hand side is equals to it is
yeah, you're looking.
yes, I'm looking.
Okay.
Okay, one more second.
Okay.
Oh, okay, it's just 3k plus 1 to the power of k plus 1 minus.
Okay. So you say 3k, 3 to the
Plus
power k
1 min,
plus
minus
1
3
minus
all
3
over
all over
2.
2. No, there's something missing.
Missing.
There's something missing.
Oh, k plus 1 plus 1.
Plus 1. Okay. A plus 1 plus 1. So this will be in brackets. Okay. So it will simplify to become
3 to the power of k plus 2 minus 3 all over 2.
2. Can we simplify this further?
Then
No, not really. So it will stay. So this will be our answer that we want, right? So write it down. 3 to the power k plus 2 minus 3 over 2.
okay.
So that's the right hand side. Okay, so now since we were stuck when we did the right hand side, now we have a better idea. We want to reach here. So we check, okay. So since you wrote it down, so now check, okay, from here, how can I get to here? Any idea?
No.
No idea. Because minus 3 we have minus 3 there. Yeah. Over 2 we have over 2. But here it says 3 to the power k plus 2. But we don't have anything like that. The only part that is this part. So that meaning that this somehow has to give us 3 to the power k plus 2. But how? Oh, that's the
I
question.
understood that. I'm saying I don't know how.
Okay, okay, cool, cool, cool.
'Cause,
Okay.
um,
You want me? Should I give you the answer, or you want to
yeah,
try
you can give the answer.
a little bit long? Okay. So when we add 3 to the power k plus 1 plus 2 to the power 3 to times 3 to the power k plus 1, we get 3 times 3 to the power k plus 1. Why I'm saying that? It's because we can say let 3 to the power k plus 1 be equal to y, for example. So it now it's going to be y plus 2y minus 3 over 2. Then y plus 2y, we get 3y minus 3. Then we substitute back. Does that make sense?
Mm-hmm.
It
Yes.
makes sense. Okay. So since we have 3 times 3 to the power k plus 1, okay, what do we do next? We want to get 3 to the power k plus 2. What do we do next?
Said we want to get rid of.
Okay, so we are saying we want to change this, right, to give us 3 to the power k plus 2. That's the only missing piece.
Yes.
That's the only thing. So
You
how
just
do we do that?
multiply 3 times 3 to the power of k plus 1 will
So,
be 3 to the power of k plus 2 because the exponents add up.
okay, so can you provide a step in between that can show us, because you are just saying from this to, can
I
you show
can't
us?
say a step in between. I said I can't say
Sorry.
a step in between.
Okay, so when I meant step, I was thinking of you saying 3, right, to the power 1 plus k plus 1.
I was
I
gonna
think you
say, but
said
I
that,
said
but
that.
I wanted. Yes, you did say that, but yeah, I wanted like you to say it out, like 3 to the power 1 plus k plus. Okay, uh, is equals to 3 to the power k plus 2 minus 3 over 2. Cool. Any
Please go
questions
back up.
there?
Up. Yes, please.
More up.
What did we do to our 2?
Okay, so which
Mm-hmm.
2? This 2. So what happened is that in my mind, I if it was me, I was going to do this direct from here to here, right? I was going to do it direct. Why? Because I noticed that 3 to the power k plus 1 plus 2 times 3 to the power k plus 1 is the same thing as saying y plus 2y minus 3.
Mm-hmm.
Because in my mind, I saw that. So now so I'm just saying y plus 2y.
Mm-hmm.
Then I get
Okay.
y plus 2, and then I get 3y. So the 3, so now the 2 is no longer there, and we have combined the 2.
Yeah.
So so this is how they will trick you a bit. You'll be thinking this is not a quadratic, or it, sometimes it would be like a quadratic as well. you would have in a similar scenario, you would have what you call 2k plus 2, so 3 to the power 2k plus 2 plus 2 times 3 to the power k plus 1 minus 3. Then you'll be thinking, how do I find this? But actually, it's actually a disguised quadratic equation, because if you take out the 2,
It's
if you take out
y
the,
squared. Oh,
yes, it will give us, will it give us y squared?
no.
No, not really y squared. It's not. It's not really y squared, but you get
Yes.
what I'm trying to say. Yes. So usually they would use such stuff to trick you. So yeah, you have to be careful in such scenarios. But yeah, did this make sense? Okay. So let's do this one. Let's do this one. Okay. So the only thing that I'll have to say is that you are just going to ignore. So from this is exactly the same thing. You're just going to ignore this part. You're just going to say, okay, I see you, but I'm not going to
Okay.
use you. Unless if you're going to use this part which is inside 2i minus 1, and you're using your part. It's not it's everything that you need is already there on the others. So yeah, that's all I can say. All right, tell me what
We are going to prove for n equals 1 and then say the left hand side is equals to 1.
So we said the left hand side is equal
1.
to 1. Okay, right hand side
And then right hand side is equals to 1 squared.
1 squared. Okay.
And then we say the
Next,
statement is true when n equals 1.
the statement is true. Oh, the previous one we forgot to write our statement.
Mm.
N is equals to 1. Okay. Next,
Next, we prove for n equals k.
for n is equals to k.
Then we say
What do we
1 plus 3 plus 5 plus ellipses plus k is equals to k squared.
3? Mm-hmm. Okay. What's next?
Next, we say, or we prove for n equals k plus 1, and then we say the left hand side is equals to 1 plus 3 plus 5 plus ellipses plus k plus k plus 1.
Plus k plus k plus 1.
And then
And then
we calculate k squared plus k plus 1.
okay, what do we do now?
The factorize.
Hello? Factorize. Okay. Can we let's try and factorize. What are we gonna write?
Mhm. Mhm. I don't know what to do.
Okay. K plus K plus 1. Okay. Okay. Let's do this, right? We wrote this which is equals to K squared, right? But for K plus 1 term, right? K plus 1, I think the only scenario where this is kind of where this is kind of where this is kind of different is that there's a slight difference, right? I'm going to show you where the slight difference is. The slight difference is that here we're given like the equation, right? We're given like the formula for the left hand side, right? Formula for the left hand side. Here also the formula for the left hand side, right?
Yes.
So in this scenario, when we are writing our what you call when we are writing our last term, right? When we are writing our last term, we should use this to write our last term because we were used from from the previous ones we were using the formula so that we get our K plus 1 term, right? So we're using the formula to get our K plus 1. So that's where we got 3 to the power K plus 1. So I think we should do the same thing here. Does that make
Mhm.
sense? Because this is a bit different from the other ones because we are using a summation notation. So since we are looking for, so since we got the the summation from 1 all the way up to K, we just want the term K plus 1, of which it's not right just writing K plus 1, it's actually derived from here.
Mm.
Does that make sense? Okay. So meaning that what do we write? So meaning that we are not, so meaning what do
2k
we write?
minus 1.
2, 2k
Minus
plus
1.
1 minus 1. So 2k plus 1 minus 1. Okay, so we have k squared. What do we get inside?
K squared plus 2k plus 2 minus 1, which is equals to 1 plus 1. K squared plus 2k plus 1.
K plus 1. Okay, now we reach here. Can we factorize
Yes.
this? Okay, what do we get to factorize?
That's k plus 1 times k plus 1.
K plus 1 times k plus 1.
Yes.
Uh, which is okay. Can we simplify this
No.
further? Okay, we'll leave it like that. Right hand side, what do we
For the
get?
right hand side, we say right hand side it's equals to um 2k plus 1 minus 1. Yes.
Right hand. This was supposed to be left hand.
Oh, I see, I see. Okay, so it's just k squared. K plus 1 squared.
Uh, yes, k plus 1 squared. Okay, k plus 1 squared. Okay, is our left hand and right hand the
Yes.
same? It's the same. Okay, so you could also just put it
Yeah.
the same.
Then we say this is true. This statement
If
is
this
true.
statement is true,
Is true when n equals 1, n equals k, and n equals k plus 1.
k plus 1. Okay, so yeah. Um, okay, so that's a very tiny detail that hopefully you remember. But yeah, uh, that's when you're looking for the last term, you actually use this because it has the formula that they use to get the term. So yeah. Any questions? Okay. Also, the thing that you should note is that if you look at this, right, at this equation, and if you look at uh, it's actually this summation. It's actually this summation. So it's actually this summation. So meaning that we actually proved, right? We actually proved uh, for this, the one that this scenario that we're talking about. So we actually proved. So I'm not sure if there's any question
No.
that you have. Okay. Um, so I think that's all that you should need to know. There's this one that I don't think that you're going to
Okay.
use. I don't think you're going to do a question like this unless if we see in your assignments that there's a question like that. But no, so far I'm not sure that you do a mathematical induction to prove an inequality. No, I don't say that.
Okay.
Okay, so so from so from let's check the. Let me open the assignment. Yeah, the assignment. So um, number one should be able to do A, B, and B. C, we haven't reached that far. For number two, you should be able to do the whole A, B, and C. Question 3, you should be able to do A, B, C, and D. Question 4, the only thing that I can see is A. Question 4, A. Question 5, you'll be able to do B. I think you'll be able to do B. Yeah, you should be able to do B.
Can I?
A, I'm still.
No, I was going to say I
Sorry?
wanted to try and complete it on the weekend of the 16th, 17th.
Okay. So yeah. So still, I haven't seen anything about this.
Mm.
Still, I have to keep on digging because I have to find where does it say, because it has to be in there. If it's not in there, then how many other stuff are not in the tutorial letter or study guide? So that's my biggest worry right now. But I might ask my sister because she has done this course with she's done this same course last year. So I might ask her if she has ever come up with something like this whereby something is in their assignment but they haven't, it's not written, because yeah. But sequence, we have done sequence, so
Okay.
Yeah. So but that's a good part of like more than half we are able to do. I'm sure you've seen more than half we are able to do. See, which one is this? 9, 12. So 12 marks out of 50. That's the ones that we right now. If we say we are writing now, we are not able to get because we haven't reached that far.
Okay.
Okay, but yeah, 38. Yeah, we should be able to get.
No.
Any question? Okay, so it's okay. Tomorrow, what time are we starting?
Just before 12. Can say 11:30 or 11:45.
Okay. Which time should we? You should choose which one, 1:45 or 2:30.
Anytime, I was giving you the options because I want to be done by 1:45.
Okay, so maybe
Okay.
1:30.
Let me write that down.
Okay. Okay. Since we before we end, how is this topic not
Yes,
much
I actually
better?
quite enjoyed it.
Okay.
I
Quite
quite
enjoyed.
liked it, I mean.
Okay. Okay. Yeah, enjoyed is a very strong word.
Yes, and I mean it because I don't like maths, so I did enjoy it.
Okay. No, yeah, that's the thing. Maths sometimes needs it's all about
Mm,
presentation. Not just maths, just school
yeah.
in general. School in general. Yeah, it's like one of the things that I actually tell a lot of people that it's all about the presentation. School can be fun. You now have to present it in a way that's it's more digestible to the
Mm,
user, that they can use something that they learned today, but also easily
mm,
apply it. It's it's so nice when you learn something, then you apply it there and then. So, oh, can you see the drawing that I made? I learned it from this method. I learned it from our classes. Uh, and yeah, that's where you tend to it starts becoming
mm,
less boring. Yeah, so yeah, that's like my biggest thing, that yeah, schools school can be fun, and not everyone is what can I say, stupid or below average in terms of grasping things. Because we would say, I know is academically
yes, I was studying. I
is not.
still kind of am convinced that I'm mathematically challenged.
But so far you're doing quite well. So that's where it's even though you have done this, like this must
Mm,
be the third time,
fourth.
right?
Well, I'll say third because I
This is
dropped the module in
fourth.
first year, so it is the third time.
Okay. So it's like the third time, but you're actually understanding quite well, quite well. And you are even noticing when I mess up sometimes. So which is which is not something little that we have that we can overlook. It's actually something that you should take pride in. That there was this one day where I told my lecturer that
Mm,
say yeah, you messed up here, and yeah, it's kind of proof. It now depends now on the
mm,
way you see stuff, the way you see stuff. Yeah. So the way you see, and you can apply this anywhere else. Like it depends on how you view
mm.
stuff. So uh, last thing is that I want to tell you of a a true story that happened to me when I was still in. Uh, I'm not sure if I told you. You might answer if I told you that I was doing geography at high school, and we used to do map work. We used to do map work, and I always got it wrong because I was there was a formula that they always used, so it was vertical interval,
Oh,
or
that
is it
one.
distance, or
Yeah.
is it horizontal distance?
I said I remember it. Well, I do geography now, so yeah, that's the one.
So yeah, so it's or is it horizontal distance over vertical interval? I couldn't like remember, like be so sure that I remember I would always
Mm,
mix myself up, and then that caused me to fail
mm.
every time. So now when we were like 2 months before writing our final examinations, our ordinary levels, uh in maths we learned we learned geometry, and we were doing gradient in geometry. So now after the lesson I just sat down and thought, the the gradient in that we learn in maths, is it the same thing as the gradient that we learn in
Mm.
geography? So now in my mind I'm thinking, okay, so now I'm picturing the xy plane. Then I'm saying x is my horizontal distance, right? Then y is my vertical. So in the formula of maths, we say y2 minus y1 over x2 minus x1. So y2 meaning the vertical, then x meaning the horizontal. So it's vertical interval of a horizontal distance. And then just by using that knowledge that I had, which I understood very much in mathematics, it made me remember every time that okay, I will never mix this up ever again. Why? Because I viewed the whole thing from a different lens, from a
Perspective.
different perspective. Yes, so that's what I also believe, like in learning and also maths, that sometimes the perspectives it differs. Differs from person to person. So my perspective is different from yours perspective. But if I force you to learn it from my perspective, that will mean you most likely you're going to fail, and most likely we're going to say that you are challenged
Mm-hmm.
mathematically. You are challenged because I'm forcing you to learn it my way, of which there's a certain way that you can understand the topic or the question or the problem. But the only problem with that is that we have to wait. It take a lot of time trying to find, okay, well, which perspective does Ledwina understand this topic?
Yeah.
So yeah,
Okay. Thank you.
okay. So yeah, have a nice day. Uh, and yeah, change your perspectives if there's something that doesn't go right.
Yeah, I'm
We'll try and
honestly,
do
I'm
better.
trying.
Yeah,
But thank you. I hope I keep understanding my girls. Or maybe not
yeah,
understanding. I think I understand during the lessons, but I forget as soon as I like have to do it by myself for things words.
yeah. That also that also comes from because you maybe if there's a way to tie something. Maybe it comes from because you haven't found a certain system that you tie it to. Like for example, like the scenario that I gave, right, is that every time I think of gradient in geography, I think of the gradient that has in math. So I have like what you call a
Mm-hmm.
reference, a reference. So maybe because you haven't built a reference, it kind of takes time and a lot of like thinking, which maybe you do or you don't have, but you'd need a reference, and references are very useful. Even like even also like in like remembering names. Like the church that I go to, it's so big that every Sunday I would meet someone new. Every Sunday I would meet someone that I and you and since you're constant and since I was constantly like learning new names and then forgetting the next week when I see that person, then I want to call them by the name, then I forget. And then it kind of comes like awkward, like an awkward situation because you keep on forgetting their name. So what I constantly like intentionally do is when I learn your name and I know that I will most likely forget your name, I try to find a reference that helps me to remember your name. So, for example, there's this girl named uh, Marine. So her name is Marine, and then her sister's name is Juliet as well. So I built a reference like, okay, if I forget Marine's name, I'm going to think of Ushaka Marine World. Ushaka Marine World. So when I think of, then I forgot, okay, what's your name again? Then I think, okay, Ushaka Marine. Okay, Marine. Yes, Ushaka Marine World. So your name is Marine. Juliet, I think of Romeo and Juliet. And Romeo and Juliet is very easy because uh, there's a car named that uses my name, Alfa Romeo, the car. So I think of myself, I think of the car for Romeo, then it gives me Romeo and Juliet. Then I can say, okay, hi Juliet. So you see, that's the power of references, which in maths maybe it will take a little bit of time for you to, okay, how can I remember this and not
Mm.
forget this?
Okay.
Yeah, so yeah, yeah. Any
No.
other question? Okay, cool.
All
See you
right. Bye
tomorrow.
bye.